Hello friends, my name is Sonu and today we will prepare a video on the distribution law. It is observed that when a solid or a liquid is added to a mixture of two immiscible liquid, in both of which it is soluble, example iodine to a mixture of carbon disulfide and water, or succinic acid to a mixture of ether and water, it distributes itself between the two liquids in such a manner that the ratio of concentration of the substance in the two liquids is always constant at constant temperature. These observations were made by Berthollet and Jagefish in 1872. However, it was pointed out that by Nernst in 1891 that the ratio of the concentration is constant only when the solute has the same molecular weight in both of the solvent. Hence, the generalization was put in a proper form by Nernst is called Nernst distribution law. It states as a solute distributes itself between the two immiscible solvents in such a way that the ratio of the two concentration of the solute in two solvent is constant at constant temperature, independent of the presence any other molecular species, provided that the solute has the same molecular state in both of the solvent. Thus, if a solute X distributes itself between the two immiscible solvent A and B, then if X remain in the same molecular state in both of the solvent, then concentration of X in solvent A divided by concentration of X in solvent B is equal to K, which is a constant. This K is also called distribution coefficient or partition coefficient. To test the validity of the law, different amount of a solution of iodine may be added to a mixture of water and carbon tetra tetrachloride or CS2 taken in different bottle. These are then shaken and allowed to stand. A known volume of each layer is pipetted out and then titrated against hypo solution to find out the concentration of iodine. Similar experiment may be performed with other solute and immiscible solvents. Now we consider about the condition under which distribution law is valid. First, the temperature must remain constant throughout the experiment. Second, the two liquids should be mutually immiscible. Third, the amount of solute added should be small. The solution should be dilute. This is essential because in certain cases the solute added affect the mutual solubility of the solvent. Fourth, the solute must have the same molecular state in both of the solvent. It should not undergo association or dissociation in any of the solvent or combination with any of the solvents. Thus, the law is not valid for distribution of benzoic acid between water and benzene, because it has been observed that in benzene, benzoic acid undergo association to form dimers. Similarly, the law is also not valid for distribution of any electrolyte like HCl acid between water and a non-polar solvent like benzene, CS2, CCl4, etc. because the electrolytes undergo dissociation in water. Now, thermodynamic derivation of distribution law. Thermodynamic derivation of distribution law is based upon the principle of that if there are two phases in equilibrium, is that two immiscible solvents containing the same solute dissolve in them, the chemical potential of a substance present in them must be same in both of the phases. From thermodynamic equation, mu is equal to mu naught plus RT ln of A, where mu naught is standard chemical potential and A is the activity of the substance in the solution. Thus, for the solute in liquid A, we have mu A is equal to mu naught A plus RT ln of A for liquid A. Similarly, for the solute in liquid B, we have mu B is equal to mu naught B plus RT ln of A B. But as already stated, since the liquid A and B are in equilibrium, so mu A is equal to mu B. So mu naught A plus RT ln of A is equal to mu naught B plus RT ln of A B. So RT ln of A minus RT ln of AB is equal to mu naught B minus mu naught A. Here ln of A divided by ln of AB is equal to mu naught B minus mu naught A divided by RT. Further, at a given temperature, mu naught A and mu naught B are constant for given substance in the particular solvents. Hence, at a constant temperature, AA by AB is equal to constant. This is exact expression for the distribution law. However, if the solution are dilute, the activities are equal to the concentration, so that expression is modified to CA by CB is equal to constant, which is original form of the distribution law. Change in the molecular state and distribution law. As mentioned earlier, Nernst was the first person to point out that distribution law in the form of C1 divided by C2 is equal to constant is applicable only if the solute remain in the same molecular state in both of the solvent. Is that it does not undergo association or dissociation in any of the solvent or combination with any of the solvents. If however such changes take place in any of the solvents, then the law cannot be applied to the total concentration of the solute in the two phases, but only to the concentration of identical molecular species in two phases. In each of these cases, the distribution law equation is modified to discuss below. Case 1. When the solute undergo association in one of the solvents. Suppose the solute X remain in the normal molecular state in the phase 1, but N molecular if associated to form complex molecule Xn in the phase 2. Then the following two equilibria will exist simultaneously. Suppose the total concentration of the solute X in phase 1 is equal to C1 and the total concentration of solute X in phase 2 is equal to C2. Also suppose alpha is the degree of association of the solute in phase 2. Then the concentration of associated molecule in phase 2 is equal to 1 by n into C2 alpha. And the concentration of unassociated normal molecule in phase 2 is equal to 1 minus alpha multiplied by C2. Applying distribution law, concentration of solute X in phase 1 divided by concentration of normal molecule of X in phase 2 is equal to constant. So C1 divided by 1 minus alpha into C2 is equal to constant. Again applying the law of chemical equilibrium, we get concentration of associated molecule in phase 2, concentration of normal molecule in phase 2 raised to power n is equal to constant. 1 by n C2 alpha divided by 1 minus alpha into C2 raised to power n is equal to constant. Then C2 alpha divided by 1 minus alpha into C2 raised to power n is equal to constant. Taking the nth root, we have nth root in C2 alpha divided by 1 minus alpha into C2 will be constant. Dividing equation 1 by equation 2, we get C1 divided by n root C2 into alpha is equal to constant, which is exact formula. When the molecule in the phase 2 is almost completely associated, then the alpha will be equal to the 1. Then C1 divided by n root C2 is equal to constant. Now case 2, when the solute undergo dissociation in one of the solvent. As before, suppose the solute X dissolve in phase 1 without any change in the molecular state but undergo dissociation into Y, Z, etc. In the phase 2, then is showing figure 5.4, the following two equilibria will set up. Suppose total concentration of solute X in phase 1 is equal to C1 and the total concentration of solute X in phase 2 will be C2. Also suppose the degree of dissociation of the solute in phase 2 will be alpha. Then the concentration of undissociated molecule in phase 2 will be 1 minus alpha multiplied by C2. Applying the distribution law, we get C1 divided by 1 minus alpha into C2 will be equal to the K constant. Note, it is obvious that if the solute undergo dissociation in phase 1, but remain normal in the phase second, then the formula obtained will be C1 multiplied by 1 minus alpha divided by C2 will be equal to the K. But C2 plus C in the total concentration of normal as well as solvated molecule of the solute X in phase second. Thus the above equation in fact implies the total concentration of solute X in phase 1 divided by total concentration of solute X in phase second will be equal to the constant. Hence we conclude that when the solute enter into the chemical combination with one of the solvent, there is no modification of the distribution law equation except that the numerical value of the partition constant is changed. Now we see the application of the distribution law. First, in calculating the solubility of a solvent in a solvent, when the two immiscible solvents are in contact with each other and the solute is added in such a large excess, the standard solution are formed. Then the concentration of the solution at this stage will be equal to their solubilities. Assuming that the distribution law is applicable for such concentration, we will have C1 by C2 equal to the S1 by S2 will be equal to K. C1 and S1 is concentration of solvent 1 and S1 is the solubility of solvent 1. C2 is the concentration of solvent second and S2 is the solubility of the solvent second. Thus the knowing of the distribution coefficient K and the solubility of the solute in one of the solvent in other can be calculated. In studying the extent of association or dissociation of the solute in a solvent, we have already seen that when a solute undergoes association in one of the solvent, which its total concentration is C2 and has the normal molecular state in second solvent in which concentration is C1, then the distribution law of formula is modified into C1 divided by nth root of C2 is equal to K, equal to the distribution coefficient. From this formula, the value of n can be calculated either hit and trial method or the logarithm method. First, hit and trial method. The value of C1 and C2 obtained in the different experiment are put in the equation. Equation is C1 divided by nth root of C2 is equal to K. Then putting n is equal to 2, 3, 4 etc. one by one, the value of K can be calculated in each case, the number of which give constant value of for K, the correct value for n. Logarithm method, the formula for finding n is C1 divided by nth root of C2 is equal to K, equal to the C1 divided by nth root C2 raised to power 1 by n is equal to K and C1 is equal to C2 raised to power 1 by n into K. Taking logarithm on both sides, log C1 is equal to 1 by n log C2 plus log of K. For two sets of values C1, C2 and C1 dash, C2 dash, we have log C1 is equal to 1 by n log C2 plus log K and other is log C1 dash is equal to 1 by n log C2 dash plus log K. Subtracting equation second from first, we get log C1 minus log C1 dash is equal to 1 by n log C2 minus log C2 dash. Then the value of n is equal to log C2 minus log C2 dash divided by log C1 minus log C1 dash. Hence n can be calculated. Similarly, when a solute undergoes dissociation in one of the solvent in which its total concentration is C2 and has the same normal molecular state in second solvent in which its concentration is C1, then we have C1 divided by C2 multiply 1 minus alpha is equal to K. From this formula, the degree of dissociation alpha can be calculated. In predicting the distribution indicator, it has been seen that iodine distributes itself between CS2 and water with a distribution coefficient equal to 400 towards CS2. Thus, if a weak solution of iodine is to be estimated, then a few drops of CS2 may be added to the solution. As a result, a considerable amount of I2 will pass into CS2 layer and give it a deep violet color. Now the solution may be titrated against hyposolution till the violet color in CS2 layer disappear. Thus iodine act as a distribution indicator in this case. Next is in the study of the chemical equilibria leading to the formation of the complex ion. Distribution law help us to determine the equilibrium constant for any of the above equilibrium reaction and hence to establish the formula of complex ion on the basis of the constancy in the value of the equilibrium constant. As example, let us consider the first equilibrium reaction. The study of the equilibrium involves the following step. A solution of iodine in CS2 is shaken with water to find out the distribution coefficient of iodine between water and CS2. A solution of iodine in CS2 of known concentration is shaken with Ki solution also of known concentration. After the distribution of iodine is complete between the two layers, the concentration of iodine left in CS2 layer is determined. The result is calculated as follows. Suppose that initial concentration of iodine in CS2 layer will be A mole per liter. Initial concentration of Ki solution will be B mole per liter. Concentration of I2 left in CS2 layer after distribution will be C mole per liter. Distribution coefficient of I2 between water and CS2 is equal to K. As iodine react with Ki, the total concentration of iodine in free state and combined state in aqueous layer is much higher than if number Ki was present. Obviously, total concentration of I2 in aqueous layer is equal to initial concentration of I2 in CS2 minus concentration of I2 left in CS2 layer will be equal to A minus C mole per liter. The concentration of free I2 in aqueous layer can be calculated by applying distribution law. Concentration of free I2 in aqueous layer divided by concentration of I2 in CS2 layer is equal to K. But the concentration of the I2 in CS2 layer will be C mole per liter. Then concentration of free I2 in aqueous layer will be Kc mole per liter. The amount of I2 that has combined with Ki is equal to A minus C minus Kc mole per liter will be equal to the D mole per liter. Now according to the reaction, Ki will be added to the I2 and formation of Ki3. Number of moles of I2 combined will be equal to the number of moles of Ki combined will be equal to the number of moles of Ki3 formed. Then concentration of Ki3 in aqueous layer will be equal to the D mole per liter and the concentration of Ki in aqueous layer will be equal to the B minus D mole per liter. Then the concentration of I2 in aqueous layer will be Kc mole per liter. Substituting these value in equilibrium law expression, so the value of K will be D divided by Kc multiply B minus D. The equilibrium constant can be calculated. In the process of extraction, the process of extraction is the great importance both of the laboratory and the industry. In the laboratory, the process is often used for the removal of dissolved substance from an aqueous solution with the help of organic solvent like ether, chloroform, carbon tetrachloride or benzene. In the industry, the process is used to remove the impurity from the product. Basically, the process involves shaking of the aqueous solution of the substance with an organic solvent which is immiscible with the water, but in which the substance is to be extracted is soluble. After shaking, the mixture is allowed to stand. Most of the substance passes into the organic layer from the which the former can be separated out by distilling of the organic solvent. However, in order that the process of extraction may be more effective and efficient, the following two conditions must be fulfilled. First, the value of the distribution coefficient of the substance between water in which the substance is already present and the extracting solvent should be greater in favor of the extracting solvent. It is sometimes possible to increase the distribution coefficient artificially by making the substance less soluble In the aqueous phase, this can be done by the adding some substance which depress the electrolyte dissociation. In the aqueous phase, this can be done by the adding some substance which depress in the electrolyte dissociation of the compound being extracted. Thus, suppose that an organic acid which ionizes to a certain extent in the aqueous solution, the hydrogen ion concentration is increased and the ionization of the organic acid is reduced because of the common ion effect. In the solution, there will be greater amount of undissociated acid and hence the amount of extracted will be greater. Similarly, an organic base can be best extracted in the presence of strong inorganic base. The addition of salt also usually lower the solubility of an organic compound in water and thus increase the distribution coefficient. Second, the whole of the extracting solvent available should not be used in one lot, but it should be used in maximum number of installment. That this factor increase the efficiency of the extraction can be seen as follows. Suppose x gram of substance are present in 1 liter of the aqueous solution. Also suppose 1 liter of ether is available as the extracting solvent and that the distribution coefficient of the substance between ether and water is 2. Now if whole of the ether is used in one lot and x gram of amount of the substance extracted into ether, then we have concentration of ether divided by concentration in H2O, then the value of x will be 2 by 3 times of x. Thus only 67% of the total amount will be extracted in this case. Again, suppose the whole value ether used in two installment each of 500 cc. After checking with first installment of 500 cc, suppose x1 gram of the substance pass into the ether layer. Then clearly value of x will be 0.5 times value of x. Thus 50% of total amount is extracted out in the operation. Therefore the amount of substance left unextracted will be equal to the x minus 1 by 2x will be equal to the 1 by 2x. Now the 1 liter of the aqueous solution containing half x gram of the substance is shaken with the remaining 500 cc of the ether. Suppose the amount extracted into the ether to the operation is x2, then the value of x2 will be equal to the 1 by 4 times of x will be equal to the 0.25x. So the 25% of total substance passes into the ether layer is in this operation. Therefore the total amount in substance extracted will be equal to the 75%. Thus when 1 liter of the ether is used in two equal installment, the percentage extraction increased from 66.7 to 75. Similarly, it can be seen that 1 liter of ether is used for 4 equal installment. The extraction increased further to 93.75%. Next is in the determination of the degree of hydrolysis. Hydrolysis constant will be equal to the applying the law of chemical equilibrium. The value of K will be equal to the concentration of HA multiplied by concentration of BOH divided by concentration of BA multiplied by the concentration of H2O. Since water is present in very large excess in aqueous solution, its concentration H2O may be regarded as constant, so that we have concentration of HA multiplied by concentration of BOH divided by concentration of BA will be equal to the KH. Here KH will be equal to the hydrolysis constant. Since HA and BOH represent the molar concentration of the free acid and the free base produced, and BA represent the molar concentration of unhydrolyzed salt, the above expression for the hydrolysis constant may be written in the more general way. KH is equal to concentration of free acid multiplied by the concentration of free base divided by concentration of unhydrolyzed salt. So the degree of hydrolysis of a salt defined as the fraction of the total salt which is hydrolyzed. For example, if in a solution of aniline hydrochloride 90% of salt is hydrolyzed into aniline and the hydrochloric acid, The degree of hydrolysis is 0.9 or may be expressed in percentage, which is 90%. It is usually represented by the symbol H. H is equal to number of moles of salt hydrolyzed divided by total number of moles of salt taken. Expression for the degree of hydrolysis of solution of different type of salt. First is salt of weak acid and strong base. Representing salt of by Ba as usual by the hydrolysis may be represented as Ba plus H2O will be converted to BOH, which is strong, plus HA, which is weak. It is a case of anion hydrolysis. Suppose the original concentration of salt in the solution is C mole per liter and H is the degree of hydrolysis at the concentration. We have value of KH will be concentration of OH negative ion multiply the concentration of HA divided by concentration of A negative will be equal to the CH square divided by 1 minus H. It if H is very small as compared to 1, we can have 1 minus H nearly equal to the 1, so the above expression become CH square nearly equal to KH and H square nearly equal to KH divided by C, and H will be nearly equal to under the root KH divided by C, and H is inversely proportional to the under root of C. Thus the degree of hydrolysis of a salt of a weak acid and a strong base is inversely proportional to the square root of the molar concentration. Salt of strong acid and weak base. It is a case of cation hydrolysis. Proceed as earlier case, we get the same relationship as H is nearly equal to the under root of KH divided by C. Third is salt of weak acid and weak base. It involves both anion hydrolysis as well as cation hydrolysis. In this case, KH will be equal to the H square divided by 1 minus H whole square. So KH and H does not involve C. Thus the degree of hydrolysis of such a salt is independent of the concentration of the solution.